to discuss. This stuff on the right-hand side, initial velocity, final velocity, are these average velocities or are these instantaneous velocities? Does anybody know?
Average.
Okay, so one person said average, give yourself 2 points. Who wants to say instantaneous? All right, so what's changing on the right-hand side? Is it the average velocity or is it the instantaneous velocity, and why?
The average.
All right, so I heard 2 people say average. Are these average velocities or are these instantaneous velocities, and why?
It's average because one of it's between the final and the initial and you subtract.
Okay, so every single person who said something so far said average velocity is changing. So those of you guys who make that argument, I'm going to give you 2 points for that one. What's changing is not the average velocity, it's the instantaneous velocity. Guys, this is how fast you're moving right at this point in time, and this is how fast you're moving at an earlier point in time. All right, so this is your measured velocity. What's changing is your measured velocity within this time period. All right, so this is how fast you're going right at this point. So I'm driving at 50 miles per hour. I know I'm going at 50 miles per hour because I'm looking at my speedometer. And 15 seconds later, I look down, now I'm going at 60 miles per hour. So what's changing is the instantaneous velocity is changing in time. T refers to the time between measurements. All right, so I take my initial measurement here, and this many seconds later, I take another measurement. Okay, so on the right-hand side, what's changing is your measured velocity is changing. So your instantaneous velocity is changing. So changing instantaneous velocity in time is going to give you your average acceleration. Okay, just remember the concept. All right, so remember the concept of average speed. Okay, let's just get back to this one. Okay, this is measured distance over measured time is going to give you your average speed or velocity. And measured velocity, changing measured velocity over time is going to give you your average acceleration. The stuff on the right are your measured values. The stuff on the left are your average values in general. So how fast the measured velocity changes in time becomes the definition, formal definition. So proper definition or the formal definition is how fast the instantaneous velocity changes in time. How fast the measured velocity changes in time. All right, so that's what both get to use. All right, how fast the measured velocity changes in time. So you go from initial velocity to final velocity within a time period. And for safety reasons, we'll get to express it in terms of G's. So roughly 10 G's is going to be roughly 10 meters per second squared. It's going to be roughly about it's going to be a G. In the United States, we don't really express acceleration by using the British unit system. We usually talk about cars accelerating in commercials, going from 0 to 60 within 5 seconds, 6 seconds, or within about 3 seconds or whatnot. So there's acceleration expressed in terms of miles per hour per second usually. Aside from that, we will always express it for safety reasons when necessary in terms of G's. All right, pick out the best answer and put it in the chat. Put it in the chat. Okay, so MKS unit system, on just about every single person picks C, so give yourself 2 points for that one. All right, C is a good answer, so meters per second squared
are still producing.
All right, let's do a few simple examples.
World-beating cars. Their latest, the XKR, is no exception. The 32-valve V8 power plant develops 370 horsepower, capable of propelling this luxury car from 0 to 60 in 5.2 seconds.
All right, so we got this Jaguar. It goes from 0 to 60 within 5.2 seconds. So question number 5 from the handout. So what's its acceleration? All right, so the mathematics is going to be straightforward. The initial speed is 0, final speed is 60. So it takes 5.2 seconds for it to go from 0 to 60. So we want to know what the acceleration is. All right, so I listed everything. All right, the next step is conversions. So we have to express everything in terms of the MKS unit system. So miles per hour needs to be converted to meters per second. So 1 meter per second is 2.24 miles per hour. Get rid of the like units. All right, so we got the conversions. So, and then looking at what's given to you and what's being asked for, the acceleration formula, the average acceleration formula is what we will get to use. And that's it. A is already on the left-hand side, so there's not much we have to do. One of the things that you can do, which I'm going to allow you to do before you do algebra, if you have any zeros, just plug in the zeros. All right, that's simply going to make life easier when the mathematics starts to get complicated in the future. So initial speed is 0, initial speed is 0, so just get rid of that. Okay. So final speed divided by time is going to give us the average acceleration. Average acceleration is going to be 5.15 meters per second squared. For some reason, if you want to feel like you need to express it in terms of G's, obviously multiplied by the conversion factor. Or what you can do is just move the decimal to the left. And that's the reason why I use an approximation of 10. So driving this car, when it's accelerating from 0 to 60 within 5.2 seconds, you will experience half a G. All right. All right, so acceleration has direction. You speed up in a given direction, you will slow down in the opposite direction. So speeding up, it's a vector that's always going to point from a smaller to the larger velocity. In this case, it's speeding up, so it's pointing in the forward direction. So we will take that to be positive acceleration. So positive acceleration will mean it's speeding up. In this case, this thing is slowing down. All right. If the acceleration is a vector that points in the direction of larger of the two velocities, initial velocity is larger than the final one, so it's pointing to the left. We will take that direction to be negative. So it's going to give you a negative acceleration. Also, we will say if the acceleration is negative, the object is slowing down. So if the acceleration is positive, the object is speeding up. If the acceleration is negative, the object is slowing down. So these are the notations we will get to use. It's also a little bit of commonsensical. You can kind of get a sense for why acceleration is positive when you're speeding up and negative when you're slowing down by looking at the speedometer, the direction the indicator moves. When you're speeding up, notice that the indicator moves towards the right in this case. So we'll take that direction to be positive. So that's going to give you a positive acceleration. And when you're slowing down, it moves in the opposite direction to the left. We will take that direction to be negative acceleration. And the negative acceleration is sometimes called deceleration. So they mean the same thing. All right, so whenever you're ready, just pick out the best answer. Okay, very good. I see a lot of these. All right, so you guys got it. Give yourselves 5 points for this one. Acceleration, only the instantaneous velocity changes in time. Very good. All right.
We had people pouring water on the tire as we went around in a circle to measure turning radius. We also had some
up until late 1950s, the cars were almost virtually made indestructible.
large pendulums that we would pull cars onto, and by measuring the timing of the pendulum, we could determine the center of gravity of the vehicle.
Here's what I'm talking about. Imagine that you're driving by a parking lot.
Rollover testing.
All of a sudden, you realize that a spot opens up
Vehicles where
in the parking lot.
We had an elevated ramp,
and then you roll right into
pull
it.
the car up the elevated ramp and
With these old cars, you could do that.
roll over a hit.
Notice that the structural integrity of these cars were amazing. You don't see a single dent of this
To
car.
measure structural integrity of the vehicle, we've got footage of crash testing where the operator would stand on the running boards and put a brick on the accelerator, and just before he hit the wall,
I mean, they made these cars in such a way that they did not want these cars to crumble
he jumped in.
under any circumstances. So you got the tester, he just jumps out of
A
the
couple of
car,
waiting fellows who caught him while the car turned into the wall.
and there was minimal damage on these cars.
Safety issues
So they went from that to these crushable
came
cars.
to the fore in the 1950s with the arrival of faster, deadlier cars. As a result, crash testing kicked into gear with car makers putting their vehicles through a much wider range of tests.
So why did they go from these indestructible to crushable cars? The short answer is safety. So the next question is, how does making a car crushable make you feel safe, or make you safe in general? Right. Let's figure that out. All right, so the car companies wanted to know, if you're exposed to, say, about 20 Gs for a fraction of a second, or 25 Gs, 30 Gs, 40 Gs, 50 Gs, would that kill you? All right, so how do you figure that out? The only way you can figure that out is through experiments. So in 1954, they conducted this famous experiment. This is known as the John Stapp experiment
50s, years before the Pinto Accord,
in New Mexico.
little was known about the essence of a collision, how much force the driver could withstand. To find out, a seemingly lunatic experiment was carried out in the New Mexico desert by the U.S. Air Force in 1954. Scientist John Stapp strapped himself onto a rocket sled to boldly go where no man had gone before.
He started the countdown.
10, 9.
Adrenaline comes in and the heart begins to beat a little faster. Then, just as he reaches 0, you get this enormous ram against your back and feel totally helpless. You're being given the biggest kick that could be delivered.
Stapp had been propelled at a speed of 632 miles per hour and stopped in 1.4 seconds.
All right, so this is the famous John Stapp experiment. He volunteered for it. They strapped him onto a rocket sled. They accelerated him up to 632 miles per hour. And then they brought him to a stop within 1.4 seconds. Within 1.4 seconds. 632 miles per hour, for those of you guys who don't know, commercial airliners in full flight, 30,000 feet up, that's 550 miles per hour. This guy was already moving 80 miles per hour faster than a commercial airliner. 1.4 seconds, stretch your arms, and this is about 1.4 seconds. Imagine being on an airliner brought to a stop within 1.4 seconds. All right, so this is what this guy experienced. So how many Gs was it? and did it survive? All right, this is a cliffhanger at this point. So I'll take a break for 10, be back within 10. Be back by, let me check the time, 7:30. We gotta resume recording. Okay. All right, so we are resuming. Meters per second, miles per hour. All right, and boom. Okay, so get rid of the like units. So end up getting a speed in terms of meters per second. We want the acceleration. Final speed is 0, so get rid of that term. All right, so we will get a negative acceleration, which means that we will be slowing down. All right, so the initial speed divided by the time, it's going to give us negative 201.53 meters per second squared. All right, so if you move the decimal to the left, that's going to give you the G load. Okay, don't forget it's going to be negative, so it's about 20 Gs. All right, so John Stapp was exposed to 20 Gs. So what happened to him?
1950. Stapp had been propelled at a speed of 632 miles per hour and stopped in 1.4 seconds. No one has ever undergone such a test before or since.
All right, so obviously he's alive, so that's good news.
Couldn't see anything.
He couldn't see anything.
And I was looking around.
He was looking around but couldn't see anything.
I was beginning to think about seeing-eye dogs and white cane.
He literally couldn't see anything. Literally. Why? Because his retinas got detached. That a big deal. Not necessarily. You can push the retinas in, and hopefully you will recover at some point. If not, they end up in a little bit of a surgery. It happens to boxers from time to time, so that's a common thing. He did recover, things worked out.
And I was thinking to myself, now I've paid my dues. I've gotten there. I've shown them what they want to know. And from now on, life is going to...
So he was exposed to about 20 Gs. And then what he did, he kept repeating the experiments. So in this case, it was about 20 Gs. So it took himself up to 25, 30, 35. He kept doing it. Only to realize that once you get up to 25, now you start having problems. The problem is you start to break bones, but smaller bones. I'm talking about ribs. I'm talking about fingers and that sort of stuff. All right, so the car companies determined that 20 to 25 Gs is a fairly safe region. So 20 to 25 Gs is survivable up to a few seconds. So that's what they discovered. All right, so the next question is, why did he volunteer for an experiment like that when the outcome was uncertain? The reason is because he was in charge of the experiment. He conducted some animal experiments, cats, dogs, and whatnot. They were fine, so he figured that he's gonna be fine himself. So he decided to conduct experiments, and he was right. So it was survivable. And car companies got what they were looking for. What they were looking for is what's reasonably survivable. 28 to 25 Gs is a reasonable G load, up to a few seconds. All right, so 27. From pilot training, we're talking about fighter jet pilots. They are trained between 7 to 12 Gs, up to a few minutes, so we know that's survivable. We know from John Stapp experiment that you can survive up to 28 to 25 Gs for a few seconds. So that's a reasonable range. So you can survive up to that 20 to 25 Gs.